All right, hello everybody. This is your E-Day lesson for Wednesday, February 19th. I thought we'd start off today with some portals of prayer. So this is from the book of Galatians, which is Paul's letter to Galatia, 2 verses 11 through 21, but we'll just highlight this verse that they've highlighted for us. I've been crucified with Christ. It is no longer I who live, but Christ who lives in me. And the life I now live in the flesh, I live by faith in the Son of God, who loved me and gave himself for me. That's from 2 verse 20. Christ lives in us. What an honor that brings us. More than that, he is working through us to minister to those he has placed in our lives. This is what our vocation means as a Christian, that we are the hands and feet of God. What a transformative concept. As a mother cares for her baby, sleepless night after sleepless night, Christ is caring for that baby. As a person sits with a friend at the death of her husband, holding her when there are no words, Christ is comforting that widow. As a man helps his neighbor clear out the remains of a burned or flooded house, Christ is laboring with that neighbor. As we live out our vocations, mindful of God's working in us, our faith is put into action. This action, these works, do nothing to contribute to our salvation. Rather, they are the fruit of it. So what I like about this, talks about this idea of vocation for the Christian. And a lot of times we think of vocation just as like, it's our job. But here it's showing how much more vocation means than that. Luther, when he talks about vocation, he uses the word like mask. A vocation is like a mask. It's something we put on, and in this case, it's putting on this new role as the hands and feet of God. So that includes a mother caring for her baby. She doesn't have to be, working a job to do that. That's her vocation, being a mother. You can also have more than one vocation at the same time. So a person sitting at at the death of a husband, for example, that's another vocation. You are put there by God. Clearing out remains, another vocation. So all of these things, sure, our jobs are vocations, but we also have things stacked on top of that call us to other things in service to God. All right. Let's take a look at our lesson today. We are actually going to do the activity. So what you are going to do is you're going to go to student.desmos.com, just like we've always done. You're going to click log in with Google, just like we've always done. And then there is a new activity sitting in there for you. And this diagram might help you out a bit, so we'll go through it before you do the Desmos. This diagram is a diagram of an isosceles triangle. So on every isosceles triangle, we have two congruent sides. Those two congruent sides are going to be called the legs. And then the remaining side is just called the base. And we have two angles that touch the base. We call those the base angles. And how I want you to start thinking about angles is they're actually kind of defined by their opposite sides. So if I'm thinking about this angle right here, well, its opposite side is a leg. If I'm thinking of this base angle right here, its opposite sides are a leg. So yeah, the base angles are the angles that touch the base, but really they're the angles that are opposite the legs of the triangle. Finally, there's the vertex angle. That's the angle that only touches the legs, but again, I like to think of it as it's the angle opposite the base. So it's the angle that does not touch the base. It's opposite the base. So what you're going to do is there are two things on this paper. Slide 2 of the Desmos, you're going to kind of copy down what you're doing as you do it. And then slide 7, you're going to copy down some other information from that one. But otherwise, just go through all the slides and answer the questions as they have them. And then come back to this video. All right, you should have done the Desmos. I did as well. Here is what I got for slide 2. And on slide 2, we see a pattern start to emerge, right? Our base angles the angles that are opposite the congruent legs are always going to be the same on an isosceles triangle. So here I have 72.5 twice, I have 49.7 twice, I have 60 degrees twice. Now, there was a bit of a rounding error on that Desmos activity. We always got slightly below what it should be because, of course, the sum of all the angles in our triangle should be 180 degrees each time. So maybe you got 180, maybe you got 179.9 three times like I did. You could have maybe even gotten 180.1. It's all 180. Desmos is just rounding. So don't, view that as absolute, all triangles now add up to 179.9. No, they add up to 180. It's just Desmos is slightly incorrect with their rounding. Okay, and on slide 7, you did that equilateral triangle thing. And so you found that no matter how long the side lengths were of our equilateral triangle, it always has 60-degree angles at every angle. So we're going to look at the implications of that as we turn to our notes today. So, isosceles triangles, those are the first thing. We're just going to fill this out as the diagram would have us. So the two congruent sides of our isosceles triangle are called the legs. The angle where the legs intersect, so here, legs intersect, that would be the vertex angle. So that is the angle opposite the base. I guess we'll go ahead and label these. So the legs on this triangle would be leg AB and leg BC. And then the base would be AC, but they haven't asked for the base. Our vertex angle is labeled right here. It's angle number 1. All right, the side opposite the vertex angle. So this is what I'm talking about, opposite. So it's the side that does not touch the angle at all, yet it kind of like defines that angle. Because if we extended AC out, then angle 1 would get a whole lot bigger because AC would be longer. So the angle is really related to its opposite, even though they don't touch directly. So angle 1 is opposite side AC here. We call that the base. Oh, I misspelled base. That's kind of embarrassing. And this is side AC. Okay? And then finally, the angles along the base. This is what we talked about earlier. Again, we can think of them as along the base, but I really like to think of them as opposite the equal congruent sides. So these are called the base angles. And in this case, they are angle 2 and angle 3. All right, next we have the isosceles triangle theorem. So this is what we were discovering on this page. Whenever we have an isosceles triangle, then the sides opposite the legs, otherwise known as the base angles, are going to also be congruent. So if two sides of a triangle are congruent, then the angles opposite those sides are also congruent. So for example here, since we've got AB congruent to BC, I'll just write this out. Since AB is congruent to BC, then we know that angle 2 is going to be congruent to angle 3. Next, we have the converse of the isosceles triangle theorem. Remember, the converse, if we start with P then Q, then the converse turns into, it just swaps those around. So P then Q turns into if Q then P. So all this is we're flipping it around. If two angles of a triangle are congruent, then the sides opposite those angles are congruent. So since angle 2 in our triangle is congruent to angle 3, then we would know that side AB is congruent to side BC. All right. So the theorem is when we're going from sides to angles. The converse is when we go from angles to sides. All right, that does it for new stuff about isosceles triangles. Let's move on to equilateral triangles. This is finally where we get rid of that weird word equiangular. And I guess it's never really going to go away, but now we get a more acute understanding of it, if you will. So a triangle is equilateral. That means it has three equal sides if and only if it is equiangular. It has three equals angles. So remember those words in the middle there, if and only if. Those are the biconditional. So this thing goes both ways. If a triangle has three equal sides, then it has three equal angles. If a triangle has three equal angles, then it has three equal sides. So that if and only if word does a lot of heavy lifting. We've got both the conditional and the converse that are true. So to list this out on this diagram here, if A is equal to B is equal to C, then we know that the measure of all those sides, so AB, whatever length AB is equal to the length of BC, is equal to the length of segment AC. So if all those angles are equal, then we know the sides are equal. And then we can go the other way. If the sides are equal, then we know that whatever angle A is equal to whatever angle B is equal to whatever angle C is. Okay? So that is the extent of what we do on the equilateral triangle. I will add this, though. We know that this triangle has to add up to 180 degrees. So whatever angle A is, plus whatever angle B is, plus whatever angle C is, has to be 180. Well, if these are all the same measure, then it's like we just have 3 of whatever angle A is equal to, these all have to add up to 180. And then we can solve for angle A by dividing by 3. So that is going to give us angle A equal to 180 over 3, which is 60 degrees. Well, if angle A is 60 degrees, that means angle B has to be 60 degrees, and that means that angle C has to be 60 degrees. So on any equilateral triangle, no matter what the side lengths are, we are always going to have 60-degree angles within the triangle. So that'll be important once we start doing algebra with these later. Okay, congruent triangles. So this is kind of turning a page here. We're going from this idea of only sides being congruent or only angles being congruent. Well, now we're talking about triangles being congruent. So this is kind of the first example we get of using this congruent word for things that aren't just like segments or angles. We've been confused before because, we have to take the hats off of the segments to say that they're equal, or we have to put this M on the angles to say that they're equal. Well, when we talk about congruence, we're really talking about like the shape of the thing. So congruence relates to shapes, whereas this equals relates to numbers. So we want to be able to say that triangles are the same, that they're congruent. And so let's learn how to do that. Congruent triangles have the same sides and the same angles. This means that all of their corresponding parts, we'll talk about what that means later, all their corresponding parts, their sides and their angles, are congruent. So we can write out if two triangles are congruent using a congruent statement or a congruency statement. So when triangles are congruent, we write out this statement. We say one of the triangles, so the return of the delta symbol here for the triangle ABC, and then we just write the congruency symbol, and then we write the name of the other triangle DEF. It does not stop there, though. It's not quite as simple as that. A valid congruency statement must match all corresponding angles and sides. So what does that mean? Well, these corresponding angles. Corresponding just means that one angle on here relates to another angle on the other shape. So if I look at the diagram here, angle A has one arc, and that corresponds with angle D, which has one arc. So what that means is when I write out this congruency statement, I can't just throw these letters together willy-nilly. Maybe you can do that for the first one, but definitely for the second one, you've got to pay attention to which angles, which sides are equal. So since A corresponds to D, both A and D are in that first spot when we name the triangle. This shows that A is congruent to D. We could just have this statement and not have the diagram and know that A would be congruent to D because they're both in the first spot. If I look at the angle B has two arcs, as does angle E. So that means they are both going to be in the second spot. Where did my one go? There it is. Okay. And then angle C here, three arcs. Angle F has three arcs. So those are both in the number 3 spot. So this shows angles. We just worked that out using angles. I think angles are probably the easiest way to name our congruency statements, but we can also get sides from this as well. So AB, if we look at our statement, A and B are in the first and second spot. If I look at side AB, AB goes with ED. And if I look at the first and second spot on the next triangle, that's DE. It's the same thing. ED, DE, same thing. So AB is congruent to DE. If we look at the second and third spot, BC should be congruent to EF. BC and EF, yep, those are congruent. And then finally, we look at the first and third spot. So AC should be congruent to DF. And if I look, AC and DF are congruent. So we've got to pay attention to the order of the points when we make our congruency statements. Finally, CPCTC. What does that mean? CPCTC is eventually it's going to be a reason in one of our proofs, and it stands for a phrase corresponding parts of congruent triangles are congruent. So on some of the proofs later on, they're going to give us the fact that two triangles are congruent. They're just going to say, ABC is congruent to DEF. Maybe we won't even have a picture. Well, if we know ABC is congruent to DEF, then we know that each pair of corresponding parts are also congruent. So I'm going to be able to say, even if I don't have this picture in my proof, I could prove that angle A is congruent to angle D because of CPCTC. Angle B is congruent to angle E because of CPCTC. Side AC is congruent to side DF because of CPCTC. These corresponding parts are congruent since the triangles are congruent. If they tell us that two triangles are congruent, we know that they're going to have different sets of congruent parts. So that is all the new stuff for today, but let's go ahead and do some examples. First, let's look at these isosceles triangles. So remember our isosceles triangles. The big thing was that the angles opposite the congruent sides are themselves congruent angles. So if I look at these, I've got two congruent sides on this triangle. 68 degrees is opposite this side. And so that means that angle J, which is opposite the other congruent side, that's also going to be 68 degrees. Okay, it also asks for the remaining vertex angle, and the way that we find that is we just use our triangle angle sum rule. So we know that all these have to add up to 180. So 180 minus 68 has 44 degrees remaining. So 44 degrees for angle K there. If I take a look at on number 2, this one's a little tricky. They've only given us this base angle, or the vertex angle, sorry. And we know that since these two sides are congruent, the two base angles are going to be congruent, but they haven't given us either of those angles. So the way we figure this out is, again, we're going to use the triangle angle sum rule. So if I do 180 minus 106, that leaves 74 degrees for both of the angles. So both of these angles are going to add up to 74. And then remember, since they're congruent, we're going to take like 2 times angle C equals 74. So we're just going to divide by 2. So angle C should equal, I guess that's 37, right? Yeah, 37. And then since angle E is congruent with angle C, then the measure is also going to be 37 degrees. All right, finally, on number 3, this is doing our converse. So what they've shown is that these two base angles are congruent, 77 and 77, both the same angle. What that means is that the sides are going to be congruent. Remember, the opposite sides. So I'm going to go to the side that doesn't touch this angle. I'm going to go to the side that doesn't touch angle Z and mark those as congruent. Well, if XY is 12 centimeters, then its congruent side, YZ, is also going to be 12 centimeters. Make sure to use your units. And then to get angle Y, again, we're just going to do 180 minus 77 minus 77. So subtract both of those angles there, and we get 26 degrees that remain. So angle Y is 26 degrees. Okay, next we're going to apply some algebra. So now we've got X values involved. This is just our, run-of-the-mill isosceles triangle with 2 congruent sides, and that means that the opposite angles are congruent. And so we can just set 5x plus 9 equal to 8x minus 30. I will subtract the 5 first, so we'll get 3x minus 30. And then add the 30 to the other side. 39 equals 3x. And divide by 3. X equals 13. On this, we don't have to find the angle values or the side values. It just asks for each variable. So I am done as soon as I get to x equals 13. On number 5, this is the converse. We've got 2 congruent angles, and that means that their opposite sides are going to be congruent. So that means I can set those equal. 15x plus 7 equals 23x minus 17. And we'll just solve that again. So subtract the 15x. We get 8x minus 17. Add the 17. 24 equals 8x. And then divide by 8. We'll get that x equals 3. All right, number 6. Oh, man, they have not given us a picture. It's okay. Draw a picture. It's fine. No one's going to explode if you draw a picture. So draw your picture. Just make a rough, triangle. And then on this, we need to make sure that whatever 2 sides we drew to try to be congruent are called RT and ST. So I'm going to do RT, and then the remaining angle has to be S. I'll mark those as congruent. And then we have angle R is 9x plus 2, and angle S is 13x minus 18. Those are going to be congruent because they are opposite the congruent angles or the congruent sides. And then angle T is the odd one out. So we might find that later. Since R is congruent to S, I'm just going to set those parts equal. So 9x plus 2 equals 13x minus 18. Subtract the 9, or the 9x, and we get 4x minus 18. And then add the 18 to the other side. 20 equals 4x. And then divide by 4, x equals 5. So we found x, but now we need to find the measure of each angle. So I'm going to plug in my 5 into the easier term out of r or s. So I'll plug it into r because multiplying 9's pretty easy. So 9 times 5 is 45, plus 2 is 47 degrees. So angle r is 47 degrees. Angle s is congruent to angle r. So angle s should also be 47 degrees. And they gave me that the measure of angle t is 17x plus 1. I could do that. I could also just do 180 minus 2 47s. And that gives me 86 degrees remaining for angle t. So instead of plugging it in, we can just do 180 minus 47 minus 47. All right, equilateral triangles. Remember, the big deal with these was that any triangle with 60-degree angles is going to be essentially equilateral. So if it has more than one, like right here, we only have two 60-degree angles, well, I could figure out the remaining angle, 180 minus 60 minus 60. It's also going to be 60. So pretty much the rule is, if you have at least two angles in your triangle that are 60 degrees, then you know it's going to be an equilateral triangle because that remaining angle will have to be 60 degrees as well. So angle C is 60 degrees. Remember, 60 degrees is the magic number for the angles of our equilateral triangle. So since we are equiangular, that means it is also equilateral. So we can unlock this entire triangle because we know that it's equilateral. So BC has to be 9 feet and AC has to be 9 feet. All right, next we have number 8, and they've marked that JL is congruent to JK and KL. These all have one tick mark showing that they are all congruent. And so that means JK is going to be 24 and KL is going to be 24. Now, they haven't asked for any of those. They want the measure of the angles J, K, and L. Well, remember, on any equilateral triangle, any equilateral triangle is also going to be equiangular. So to find the value of each angle, it's just 180 over 3. It's always going to be 60 degrees on your equilateral triangle. Okay, and now we can apply some algebra again. So if PQR is an equilateral triangle, solve for x and for y. Remember, we want to be careful not to relate our x's to y's at all. And it actually makes it pretty easy on this one because y is our side length and x is the angle measure. So there really isn't any way we could relate the y's to the x's on this one. So if this is indeed an equilateral triangle, we know that the sides are equal, and we know that the angles are all equal to 60 degrees. So let's solve for x first. We have this one angle R is 7x minus 3, and we know that it has to be 60 degrees. So I'm going to set 7x minus 3 equal to 60. We'll add the 3 to the other side, and then divide by 7. So x equals 9 on that one. And then lastly, we find y. We know that we don't have any like numerical markers yet for what these side lengths are, but we can relate them to each other. So I could say 9y plus 1 equals 11y minus 23. Okay, subtract our 9y to the other side, add the 23 to the other side, and divide by 2. And there's our answers. All right, we're going to close out with our congruent triangle namings that we learned. So first, we have like JKL is congruent to PQR. Triangle JKL is congruent to triangle PQR. Remember the rule here. When we name a congruency statement, we've got to name these triangles so that like angle A is congruent to angle D and angle B is congruent to angle E. The first spot has to be congruent to the first spot. The third spot has to be congruent to the third spot. And then also the sides just work out to be congruent as well. So AB would be congruent to DE. BC would be congruent to EF. So we're going to do that over here. They've told us that JKL, triangle JKL, is congruent to triangle PQR. So J, angle J here is in that first spot, and it's going to be congruent to the other angle in the first spot, which is angle P. If we look in the second spot, we have angle K congruent to angle Q. And then the third spot, angle L, will be congruent to angle R. Then we have the sides. So side JK is in the first two spots, so 1, 2. And then in the first two spots of the next triangle, we have PQ. Okay, in the next one, we have spots 2 and 3 are K and L, and that's going to be congruent to spots 2 and 3 on the next one, Q and R. And then lastly, first and third spot, J and L, will be congruent to first and third spot, P and R. So these are all of the different pairs of angles and sides that are congruent just from this statement. Now, we can also write a different valid congruency statement for these same triangles. So there are a number of different ways we can arrange these. One easy way to do it is just to get a different statement is to take the first angle, or the first letter, and just kick it to the back. So if I wrote triangle, instead of J being first, do KLJ is congruent to triangle, not PQR, but kick P to the back, QRP, that would work. You could also do it again. So if you started with the original one, maybe you take the last letter and bring it to the front. So that would be LJK, congruent to RPQ. There are a number of different ways to do it. So whatever way you would like to use, that's fine. Just know this is going to be like one of the things where there are multiple correct answers because there are multiple different ways to write these triangles such that all these angles are in the correct spots. All right, number 2 is going to be your classwork. So I won't do this on the video, but it is your job to do number 2. It's a very similar problem. So go ahead and write out all those congruent angles and congruent sides, and then write another valid congruency statement, and make sure that's submitted with your classwork for the day. All right. Now this is using CPCTC on 3 and 4. So if I look at KPM, and AYC, we're going to be able to find each of these congruent sides. So for example, KM, even though we have the picture, we don't necessarily need to use it because KM is first and third spot, and that means AC is first and third spot. CY, if I look here, CY is the second and third spot on triangle AYC. And I'm going to try to keep that same order. So if I have CY here, then MP, I'm going to go 3 to 2. So MP would be my congruent side. PK on my next one. PK is 2 then 1. So that's going to go with YA on the other triangle. Angle Y Angle Y is in the second spot. That corresponds to angle P. And you can kind of see that on the diagram. If you look, this figure is just a triangle that's rotated from KPM. So angle Y is congruent to angle P. Angle K will go with angle A. They're both in the first spot. Angle ACY. ACY. Well, however you name these angles, it's going to work the same way. So ACY went 1 to 3 to 2. And so ACY goes the same way for KPM. So 1, 3, 2. KMP is going to be the corresponding angle there. So KMP would be this angle. ACY would be this angle. It looks like it works. All right, MPK, triangle MPK. So what they've done is now they're going in reverse of this naming. So MPK, they're going 3, 2, 1. So we're going to name the next triangle in reverse CYA, triangle CIA. And then they have triangle YAC, which is 2, 1, 3. So we're going to name its congruent triangle 2, 1, 3 on KPM. So 2 is P, 1 is K, and then 3 is M. So triangle PKM. Yeah. So those are all the namings, but we can also use these to figure out side lengths and angles. So if we have triangle STW is congruent to triangle BFN, then, and they've given us some measures on the diagram here, we're going to be able to find each of the missing measures. So BN here, BN is first and third. First and third is SW on the name. And if I look on the diagram, SW has a length of 9 centimeters. The other way you can do that, if we know these triangles are congruent, I can see that BN is the shortest side on this triangle. Well, if I have the shortest side on one triangle is going to be congruent to the shortest side on the other triangle. So you don't necessarily need to consult the name every single time. Let's look at maybe BF next. BF, I can see, is the hypotenuse of this triangle. And since it's congruent, the hypotenuse of the next triangle is 17 centimeters. So I know that BF is going to be 17 centimeters. And then TW is just the middle side. So if I look, TW is like that awkward middle side. It's not the shortest, not the longest. Well, the middle side on the next triangle is 14. And so that means TW is going to be 14 centimeters. I can check these by going back to my name. So TW is second and third spot, and that should go with FN, and indeed FN is the 14 centimeters. BF is first and second, so ST will be first and second. That's 17 centimeters. So we got those all correct. Next we have angle W. Angle W is in the third spot, and that goes with angle N, which is 82 degrees. Angle B is in the first spot. S is in the first spot, so 67 goes with angle B there. Ooh, and then finally, angle F, they actually don't give us anything that corresponds to F. Both T and F are blank. So what we're going to have to do is the triangle angle sum. We know that B is 67, so we can do 180 minus 67 minus 82, which leaves us with 31 degrees for angle F there. So we did 180 minus 67 minus 82. All right, that does it for the notes and the examples on this one. Go ahead and turn in your classwork whenever you're able to. And there is a homework assignment in there for you, which will be due on Thursday at 8 a.m. Have a great night, and I will see you hopefully on Thursday. Goodbye.